this little discussion is kind of get you going in terms of understanding the concept of pH and how to calculate that numerical value. Now, back in the old days, we used to have to use things called log tables and all this other stuff. Well, you guys are so lucky you got these wonderful things called calculators that you can use. And honestly, that's what I used as well back when I was in school. That's when they came out with these like the TI-30s and things like that. So I actually have my old calculator from 1980 or 81 that we used to use to calculate pH. But they also showed us how to use the log table. So you guys are pretty darn lucky. But what you have to understand here, and this comes from your textbook, I believe it's in the second section of this particular chapter. And just to lay the groundwork, normally water does not what they call self-ionize, okay? It happens to a very, very, very small degree, and we use that knowledge to be able to help us calculate pH. Right? But what you look at on that particular section is that it talks about the self-ionization of water. And it happens just a little bit, but what you'll produce, if you think about that, if you take water and you were to split it up, okay, into its constituent parts, you would come up with a hydrogen ion and a hydroxide ion. And if you notice, we did that a little while ago when we started talking about conjugate acid-base pairs, okay? And when that happens in water, okay, what you basically have is what's shown down below in this particular section. It says in water or aqueous solution, hydrogen ions are always joined to water molecules as hydronium ions. And hydrogen ions in aqueous solutions have several different names. Some chemists call them protons, others refer to them as hydrogen or hydronium ions. In this textbook, it said either hydrogen or H plus or hydronium is used to represent hydrogen ions in aqueous solutions. So when you have that self-ionization of water, okay, you don't just form your hydrogen ion. What happens is that you would have two water molecules, and that bare proton that it's referring to up here would actually associate itself with one of those water molecules to form what they call this hydronium ion, H3 with a positive charge. So those things are interchangeable in terms of hydrogen ion and hydronium for this particular reason. And that makes all kinds of sense. Once again, if you think about how water is, you've got the Lewis structure for water here. And we've talked all the time about the high polarity that this water molecule has with the partial positive ends and the partial negative ends here. So it would make sense that that bare proton that might be floating around here might associate itself and form this hydronium ion here. All right, so you have that self-ionization of water. Now then you say to yourself, why is this important here? And this may be cut off up here a little bit, and I hope it's not. But when you read up here, it says, the self-ionization of water occurs to a very small extent in pure water at 25 degrees Celsius. The equilibrium concentration of hydrogen ions and the equilibrium concentration of hydroxide ions are each only 1 times 10 to the negative 7th molar. Now, I've got that value written over here, 1 times 10 to the negative 7th molar. Okay, that's very, 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 very small. Okay, very, 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 very small. And in that particular instance, when you think about this hydronium, okay, or hydrogen ion, and the hydroxide ion concentration in distilled water, okay, in pure water, they are going to be equivalent to one another. They are going to be equivalent to one another. So what that means is this particular value over here, this particular value over here is going to be the value of the hydrogen ion or the hydronium ion. It's also going to be, okay, since they're going to be equal, it's also going to be the value of the hydroxide ion. So the product of those two is going to be this, what they refer to as the ion product constant for water. Okay, that's the K sub W for water, all right? And that is this value here. If you were to take and multiply 1 times 10 to the minus 7th times 1 times 10 to the minus 7th, you would have this particular value right here. Okay, and it's actually molar squared if you think about that, because you haven't gotten rid of either one of those two units or labels over here. Okay, so this is the ion product constant for water, and that's very important in understanding how to calculate pH. Because when we start talking about whether or not a solution is acidic or whether or not a solution is basic, and basic also refers to as alkaline, what that speaks to is to whether or not, okay, either the hydrogen or hydronium ion or the hydroxide ion is present in a larger concentration. And if we know this right here is, in terms of the ion product constant of water, so if we are looking at any one of these solutions right here, and they're trying to get us to find the value of either one of those variables, if I know the concentration of my hydrogen ion, I can always figure out what the concentration of my hydroxide ion is going to be, because I know that they are both equivalent to this particular number. So, once again, as it shows you over here, my concentration of hydrogen ions times my concentration of hydroxide ions is going to be equal to 1 times 10 to the negative 14th. Times 10 to the negative 14th. Okay, that's 14, negative 14. And that really should say molar squared. Okay, so that allows us to figure either a hydroxide or hydronium concentrate, or pardon me, not hydroxide, a hydrogen or hydronium ion concentration or a hydroxide ion concentration if given the other. That is very, very important. Well, why is that really important? Well, when you look at that concept of pH, pH is essentially the negative logarithm, all right, of the hydronium ion concentration. Okay, and if we know what the pH is of a substance, we can tell you whether or not it is acidic or whether or not it is basic. All right, if it's got a pH of 7, it's neutral. A pH of 7 is neutral. That means that you have an equivalent number of moles of hydrogen ions or hydronium ions and hydroxide ions. Okay, so those two things are equal. Okay, so that's kind of important to know there. So this little chart right here talks about, whether or not a solution is acidic. If it has a pH of less than 7, it's going to be considered acidic. If it has a pH of over 7, it's going to be considered basic. Tremendously, tremendously important. Another thing to kind of keep in mind here is that if this dude is acidic, right, the hydrogen ion concentration is greater than that 1 times 10 to the negative 7th molar. All right, and that should make sense based upon what we learned in the previous page. Okay, so once again, very, very important stuff here. I'm going to kind of wrap this one up a little bit so that you can kind of process some of the information. This was a pretty cool chart that was also in your textbook that I think that's worth bringing up. It gives you some pH ranges for various substances, that are common, around even your household and stuff. Like when you look here, for example, you look at, like, say, lemon juice, for example, has a pH range, around 2.5 or so. It's pretty acidic. Here's a cool one for me too, black coffee. pH range of 5.0. And I have not looked, but also you have to remember, like your pop and things like that, your soda, there's some phosphoric acid in a lot of your colas. So that's an acidic environment. That's why it can be hard on the enamel of your teeth and so on and so forth. So there's a lot of neat things in life as it relates to, what about pH? You look at things like on the other side, on the basic side of things, like household ammonia, washing soda, milk of magnesia. You look at milk of magnesia and also things like Tums, some magnesium hydroxide. And, you'll take those kinds of things to help actually raise the pH inside of your stomach. Because when you look up here, it says, 0.1 molar hydrochloric acid in gastric juice. Okay, they're pretty close to this being the same right there, because honestly, we've talked about this before. In gastric juice, the liquid inside of your stomach that has hydrochloric acid. So so you have to have a low pH range to activate the enzymes that are going to help break down a lot of the proteins in your food. So that's kind of cool. Okay. Also, when you think about it from an agricultural perspective, pH is pretty important because you want to have the proper pH ranges to be able to grow your crops and stuff as you want to. If you go back and look at that fertilizer manual on page 2, there is a pH chart basically that shows the ranges for the different types of fruits and vegetables, especially they have vegetables there for the most part that are pretty common. For example, blueberries, a pH range of 5.0 to 5.5 is what they say that they like. In another sample that I read, it actually said a pH range of 4.09 to 5.0 for blueberries is more effective. Okay, so farmers have to know about this in order to be able to augment the soil to either raise or lower the pH depending upon what kind of vegetables or crops that they want to grow there. So there's a ton of things that you can explore with respect to pH, and it has such a wide-ranging impact on our everyday lives. We just don't even think about it. Like I said a minute ago, you guys drink pop. Some of you drink a lot of pop, so you're drinking a lot of phosphoric acid. Well, oh, acid's terrible. Well, yeah, it does destroy the lining of your esophagus and things of that nature. But always remember, you have gastric juice in your stomach too, so you do have acid in you. And you also have some buffering systems in there, which is something we'll talk about later. Have fun with this.